Hey all, welcome to Share Trick. This is Raj here. Friends, you might have got tired as I keep on repeating in most of my videos the constraints of CRISPR editing system so that we have a realistic view of valuation. The key constraints, as you know, are a delivery mechanism, off-base edits, and the inherent mechanism of double-strand breaks to try to repair themselves, leading to gene shuffling. Today, I come to you with some good news on the prospects of reducing these constraints, at least a little bit. So let's get started. Welcome back, friends. As regulars of this channel, you know that we have had some improvements in delivery technology with the advent of liquid nanoparticles. We still have delivery constraints depending on specific areas of the body that are the destination for the payload. However, we also know that AAV and lentivirus have their own limitations, and potentially AAV might no longer be used going forward as a delivery mechanism. The other problem we have is also the tendency of the double-stranded breaks to try to repair themselves, and sometimes that leads to gene shuffling. Also, there are repeat points on the DNA that can cause cancer if edit happens anywhere near them. I think that the fact we know this reduces the risk to a good extent. The solutions to these problems are also ongoing, and for instance, base editing avoids the double-strand break altogether, but these edits are smaller. And when it comes to larger edits, we have the problem of mosaicism, which I spoke about in a separate video. It was an entirely separate video dedicated to mosaicism and how it causes a problem with gene editing when large edits are performed. So in my opinion, diseases that require less than 3 genes to be edited are well within our capability to address, while larger edits are still a matter of risk. And within these 3 edits, again, off-base editing is an issue for us. However, we are seeing new technologies being deployed, and a key test is Excision Bio's EBT-101 that I'm watching very closely. It's performing well so far, and it has massive edits on the HIV DNA. We will get to hear results before the end of the year, and I hope it comes out successful. So that will show that we have found a way around. And now I have more good news, and this is coming from the University of Copenhagen, and this pertains to off-target cuts. It so happens that University of Copenhagen and Aarhus University have been collaborating on research into understanding the CRISPR mechanism in more detail than what we already have, and with a view to find reasons behind off-target edits. Professor of bioinformatics Jan Gorodkin, whom you see up here, is in the Department of Veterinary and Animal Sciences, and he said that we now are able to explain why some off-targets, which is unintended, cuts elsewhere in the genome in a more effective fashion than on targets, which is the cut at the intended place. We also have learned how different DNA sequences around the on target can impact how efficiently the Cas9 protein cuts the DNA. Hopefully, this knowledge will pave the way for more effective and safer use of CRISPR. One of the studies sought to determine the best way for the guide RNA to attach to the DNA, making the cut as effectively as possible. Because if the cut is not sufficiently effective, the scientists may not be able to edit the DNA properly. One of the premises that informed the study was that CRISPR does not really work well when the bond between guide RNA and DNA is too weak. What they learned in this study was that if RNA and DNA bond was too strong, that was also problematic. And the study came up with the realization that in both the cases, the gene Caesar will be too weak and ineffective, or too strong and ineffective. And therefore, the study came up by calibrating the bonds, and they prescribed a Goldilocks strength of the bonds between guide RNA and DNA that would cut just right for the edit. The study also had identified the optimal position of Cas9 protein for achieving the most effective cut. Because before Cas9 is able to cut the DNA, the protein must bind to a specific part of the DNA string. DNA consists of 4 different nucleotides, A, C, G, and T, and Cas9 can only bind to a sequence with 2 consecutive G nucleotides. The researchers have identified the effect on Cas9 of multiple consecutive G nucleotides, a situation where it is hard to hit the target because every 2 consecutive Gs compete for binding with the Cas9. This means that when there are several Gs upstream, that is before the sequence that Cas9 was intended to bind to, the cut will be more effective. But when there are several Gs downstream, that is after the intended sequence for Cas9 to bind to, that cut is less efficient because every subsequent G is competing with the previous subsequent Gs. Well, that's not all. There was a second study that focused on off-targets. Here, the researchers developed a new method for measuring the effectivity of off-targets when that was not available much before. This new method enabled the researchers to test 8,000 potential off-targets for 110 CRISPR guide RNAs in the process of being translated into human medicine. They found that the earlier estimate that around 10% of 8,000 potential off-targets were in fact off-targets. That means that all the 10% that was expected to be off-targets before actually manifested during the translation into human therapy. Additionally, they found that far more off-targets than they would have been able to find with the traditional methods, and with the new methods, they found even more off-targets. This means that the off-target percentage is much higher than we thought. Think of this as the risk of new therapy being higher than we anticipated before. The risk of new therapy failing is much higher than what we anticipated before. Further, the study identified 37 of these off-targets are located in cancer-related genes, which increases the risk that developing drugs that require edits in these 37 areas will become harder or even impossible, as even unintended cuts in these genes may lead to cancer as a side effect. So with all that said, what does this all mean? So here are my conclusions. I think that as this is a great development, as more researchers digest this information, we can expect new best practices for gene editing that will raise the floor of targeting and precision of gene edits. This will also help many genomic companies redesign their approach with this new information and reduce the risk of failing in clinical trials. Apart from this, knowing the 37 targets that are carcinogenic will help avoid wasting time and resources on therapies that will work on those on either intentionally or unintentionally. So all of this is going to help us to find much more efficient targets to put into the pipeline so that they have greater chance of success. Understanding the Goldilocks strength between guide RNA and DNA will help improve the probability of success of gene editing significantly. And this can also lend itself to the therapy research and therapy design so that gene edits are much more effective. These are still early days, and I think that the results that this study should show up, results of this study should show up in the pipelines over the next 12 months. Thanks to our subscriber Max Immunity for bringing this article to my attention. A link to the article is in the description, so you can choose to read the source and form your own conclusion. And if your conclusions are anyway different from what I have concluded, please put it in the comments below so that we can make necessary corrections in future videos. As always, please do not hesitate to press the like button if you like this video. It helps the channel. And in case you have not yet subscribed, why not? We are waiting for you to subscribe and help us grow this channel. Press the subscribe and notify button so that you see our daily new videos, and you can choose to watch them immediately or at a later time. Thanks and have a great day. Bye for now.